was already doing now because before we had. So this is already in Zoom. Do you see it in Zoom? Okay.
Okay.
All right. So then looks good. And the topic of the presentation will be smoke interaction and interacting with all the gases.
Okay. Thanks a lot. Sorry for the delay. Thanks a lot to the organizer for this invitation to this beautiful meeting and place. I'm Pietro Massignan. I'm working in the Universitat Politècnica de Barcelona. And today I'll be presenting recent works on superfluid fraction of interacting Bose gases. So I will just, as an outline, I'll just give a brief introduction to two fluid hydrodynamics and what is the superfluid fraction F. Then I'll discuss bounds introduced by Leggett to this quantity for dilute quantum fluids. And at the end, I will also discuss the validity of these bounds for general many-body systems. So let me start by acknowledging my collaborators in this work. First is Daniel Perez, a very talented master student, which now moved for his PhD to La Laguna in Tenerife. And Grigoria Strakarczyk is my colleague at UPC. Okay, so what is superfluid? Superfluid is a very peculiar state of matter. It needs a quantum description of it, as we now know. And this is a state that is characterized by just vanishing viscosity, which means that we can have persistent current and dissipation flow in the system, as was discussed by Kapitsa already in late 30s. And to describe it, we need a macroscopic wave function psi, which is a complex wave function that has a well-defined phase across the whole system. And a characteristic of superfluid is that their velocity v is can be written as the gradient of this phase phi. And therefore, this means that the flow is potential because the velocity is the gradient of some phase field. And it's also rotational, so the curl of the velocity is zero. This follows immediately because the curl of a gradient is always zero. This has a profound consequence, and that means that actually the circulation in superfluids is quantized. So if you calculate the line integral of the velocity along a closed path, you always find that 2 pi times h bar. So if you want Planck's constant h divided by m times j, and j is an integer that basically counts how many vortices are within this closed path. So this is a fundamental difference between quantum vorticity and classical vorticity. In a superfluid, the vortices must be quantized. Okay, so superfluids were described, superfluidity was discovered in liquid helium first, but it took a while to understand it. So some groundbreaking description of these systems came by the seminal works of Tisla and Landau, who introduced the so-called two fluid models. So they said, okay, if, that actually these fluids can simultaneously exhibit some normal and superfluid properties. And this means that so if you want, the current J, the mass current J, can be written as sum of two contributions, a normal and a superfluid contribution. It's a current, so it's a density times a velocity. But so in this description, which is a phenomenological macroscopic description, we separate the system into this normal and superfluid component. Each of them has a separate density and a separate velocity. And as a consequence, there exist two sound modes. So the first is a density wave in which the two densities oscillate in phase, rho n and rho s oscillate in phase. And this has the usual sound speed, which is the square root of the g times n, the interaction parameters times the density. But there can also be a temperature or entropy wave, and that's the one that is realized when rho n and rho s oscillate out of phase. And this is the so-called second sound, and its speed is slower than the one of first sound. This was, in the context of cold gases, was very nicely observed in an early work by Rudy Grimm, in the group Rudy Grimm. So they basically excited the gas with some parametric heating in a small region, and then they observed that as time went by, they observed the propagation of a kind of shock wave, but also of a dip that moved in the density that moved to a slower velocity, and these are exactly the first and the second sounds in this system. Okay, so we are all familiar with the fact that VECs are depleted by strong interactions. So if you have n particles in the system and you look at these are bosons, and n0 of them condense to the ground state, and the difference between n and n0 is Bogoliub's theory tells us that it's the proportion to the square root of the gas parameter Na cubed. We also know that uniform VECs, unitary superfluids, and even liquid helium-4 at T equals 0 are fully superfluid. So this is one, striking demonstration that superfluidity and condensation are not the same thing. Okay, so when does a normal component arise? Well, it can arise when we go away from T equals 0. This is also familiar. So non-zero temperatures, the normal density grows as T over Tc to some power. Alpha is 3/2 in a uniform 3D gas, or it's 3 in a three-dimensional harmonic trap. So this, as you increase the temperature, the normal component rises as a power law. But it can also be non-zero when you have breaking of Galilean or translational environments. So this was maybe not familiar to me when I started to work on this. Importantly, this breaking of translational Galilean invariants can be externally induced, so by an external potential, or can be spontaneous, as in the cases of supersolid. So we'll discuss later. Good. So what is the superfluid fraction that I introduced before? So the superfluid fraction F is defined as the superfluid density divided by the total density. And it's a response to a drag. So what I do is basically I have a system, and which is this blue box, and I put it on some conveyor belt which moves with velocity v, and I check the momentum p of this. If the system responds, it's kind of a normal system. If it doesn't respond, it's a superfluid system. In particular, so being a response to a force, this F is actually not a number. This was another surprise to me, but it's actually a tensor, because I can pull the system in one direction and can get a response in the other. So in general, F alpha beta is can be defined as 1 minus the limit of the average momentum in the system divided by the momentum that I would basically have classically. And again, alpha and beta are two indices that can be x, y, or z. Okay, in time reversal invariant systems, there is no transfer response. So transfer response is usually the whole response. But if we don't have breaking of time reversal symmetry, then this tensor is diagonal. So it's, if you want, is a vector. And through this system, I will only consider a drag along x, and then I will just denote f of x. Right? Okay, so one other remark is that if we have a moving fluid, a reduced superfluid density means a reduced mobility. And so it can actually be shown that F, this ratio here, can be also written as the mass of the bare atoms divided by the effective hydrodynamic mass. So maybe you're more familiar with this M star if you want. Good. So what about the Leggett bounds? The Leggett, so superfluid is a dynamical response to the system, but actually Leggett showed that one can derive two bounds to this quantity based on just the particle density, so the modulo square of psi. The upper bound F plus, I'll give here the expression, I'll come back to that later, so don't worry too much about that, but this is a variational expression, so it's a strict upper bound to the superfluid density. The lower bound F minus only goes for fully condensed systems, so systems in which the system can be written as a product of single particle wave functions. So this lower bound can be violated. I'll also come back to that later. But keep in mind that the upper bound is strict and the lower bound can be violated. An important thing is that in one dimension, or when the density factorizes as some density in the one direction, in the direction of the current, times some the density in the transverse directions, then the two bounds coincide, and therefore this expression here is actually, since one is a lower bound and the other is an upper bound, this expression here coincides with the exact value for a dilute Bose-Einstein case. Okay, so let's come to an understanding of these two formulas. So in the lower bound, I'm first taking the average that's outside is on the transverse direction, and then I take an average over the x direction. So this basically means that if we apply a current along this direction, and this is my system, and I have some potential here which is impeding the system to flow, when I do compute this quantity here, what I do is basically I chop the system into lines, into channels, and then I compute this one-dimensional legged bound, which is this internal expression, in each of the channels. So I compute this into independent channels, and then I average over all the channels, and I get a result. Since doing so, I'm basically ignoring the fact that there can be crosstalk between these channels. This kind of shows that I'm having a lower bound. The upper bound has a slightly different expression, and in this expression, so I first average over the transverse direction and then over the longitudinal direction. So in this expression, what I'm doing is I'm basically averaging the density at each value of x, so on each transverse hyperplane, and then I use this perpendicularly averaged density to compute this one-dimensional leg. In doing so, I'm basically ignoring the fact that maybe the fluid will not like to take such a winding path with very sharp turns, and this means that I'm actually computing an upper bound. Importantly, this is the strict one, and in particular, it's easy to see that if you have some region where the density is strictly zero, then this denominator, this fraction explodes, and this means that this whole number goes to zero. So if you have a nodal surface, a region in which the density is fully zero, then the upper bound is zero, and this means that the superfluid fraction must be zero. Okay, so let's now see how to compute this superfluid fraction. Within Gross-Potayevsky theory, what one can do is one can take a periodic boundary condition. One can use a potential V, which drags the system. It will only drag the normal part of the fluid. The superfluid part will remain undragged. And it will move it with velocity zero along x. What I can do is I can go into the moving frame, and then the Gross-Potayevsky equation can be rewritten in this form. So there's just the potential V becomes static, and what I get is a modification of the kinetic term. So I replace P by P minus MV0, basically. Okay, so when you do so, this is very convenient for numerical calculations, because what you do when you compute the ground state of this expression, you will see that the energy grows quadratically with V0, for small V0 at least, and this gives direct access to this F. So the superfluid function F, superfluid fraction F, is directly defined by this expression here. So this is very convenient numerically. This is equivalent to what is called the twisted boundary condition. It's basically the same. It's also easy to show that this expression here, it's fully compatible with the expression I gave before, that F was this expression here. It takes just one line of calculation and applying the so-called Hellman-Feynman theorem. Okay, so here I show an alternative understanding of this legged bounds, which was I learned from Jean Dalibart's course earlier this year. So in a fully condensed system, a phase twist of theta generates, as we saw before, an energy increase which is proportional to theta squared, and this is a purely kinetic energy. So this means that this theta is proportional to V. So a phase twist theta in a fully condensed and super system generates a particle current which is proportional to theta, and the constant proportionality is this rho s. This is clearly Ohm's law. So we can have actually an electrical analogy to this to our superfluid system. So in which we say, okay, I have two parallel plates. I put a voltage difference U between A and B. and I check what's the current I. This will be proportional to U by this G, and G will be basically my superfluid density. And I model my system by a network of elements, each of them having conductance Gij. Okay, so if I have this network of elements, I can lower the conductance by removing all the vertical elements. And in this case, I get this effective circuit here. This can actually be computed. The conductance of the system can be computed because each of the lines can be replaced by G bar J. And now I have a series of conduct elements which are connected in parallel. And the effective conductance of this is just the sum of this G bar J's, which you see here. And each G bar J is actually the inverse of the sum of the inverses of Gij. And so you see now that this electrical, the effective conductivity of this electrical circuit has exactly the form of the lower bound introduced by Leggett. An upper bound to this G can actually be found instead by replacing all these vertical elements by a short circuit. In this case, you get, I mean, doing a similar calculation, you get exactly the upper bounds that I introduced before. Good. So what about experiments? There's been 2 experiments made earlier last year, one in the group of Jean Dalibard and the other in the group of Jan Spielman. Very similar ones. I will discuss the one by Jean Dalibard's group and Jérôme Bognon's, which has also been reviewed. These 2 papers have been reviewed in a paper by Thierry Jamarchi. So what they looked is, I mean, they knew that sound hydrodynamics tells us that the sound propagates with velocity c, which is proportional to the inverse square root of the inverse compressibility times the superfluid fraction. So if you measure the sound speed, you get access to the superfluid fraction along that direction. So what they did is they took a system, a 2-dimensional Bose-Gas, in which they put a 1-dimensional optical lattice. Along the direction y, there is no potential, so the superfluid fraction is 1. While along the x direction, there is a potential, and this basically increases the effective mass. So if you want, reduces the superfluid density along the direction. And so if you're able to measure independently Cx and Cy, the sound speeds in the 2 directions, you get access to this superfluid fraction F. And okay, so by comparing F extracted as a ratio between the 2 sound speeds, which you see here as a function of the height of the optical lattice, and the value of F obtained by the Leggett bound that I introduced before, they got an extremely good pigment, as you see here. So this Leggett bound seems to work very well in this case of these 1-dimensional potentials. Okay, so when this is where I got, I mean, seeing a talk by Sandro Strengari on this argument is when I got interested in this work. So I said, okay, how can we generalize this to 2-dimensional potentials? In more than 1 dimension, these 2 bounds do not coincide because the density doesn't factorize in a many-body system. And therefore, are these Leggett bounds going to be accurate or not? So this is what we discussed in our paper that appeared in March. And I just noticed yesterday night that there's a very related work by Alberto Biella, which was put forward earlier in the summer. Okay, so what we did was we looked at superfluid fraction first in regular potential. So we started by looking at a 2-dimensional optical lattice as a function of the height of the lattice. The system undergoes a transition from a superfluid to an insulator. And here the first line is for weaker repulsive interaction. This is for a stronger repulsive interaction. This is BEC. So the stronger are the repulsive interaction, the stiffer is the system and more resistant to the optical lattice, as very intuitively one can understand. And there are some green and red lines, which are respectively the upper and the lower bound. And as you can see, they're basically identical to the exact result, which is the black line. So this lower and upper and lower bounds work extremely well in the case of an optical lattice. You see here in the zoom, I mean, it's absolutely perfect. We looked at a slightly different potential, some square grid of repulsive columns. And here is the result, the numerical result. And in this case, the two bounds are slightly shifted. But still, I would say the agreement is quite high. So again, this upper and lower bounds are computed directly from images of the density of the system, which is something that is readily available in all experiments, ultra-cold experiments. And the dotted lines are some weak coupling approximation derived through Bogoliubov approximation. Then we started looking at some hybrid potentials. So that by hybrid, I mean that the potential is different along one direction and along the other. So we took the cross product of a lattice along one dimension and speckle along the other direction, because we wanted to check whether whether the superfluid fraction is indeed a tensor. And to do so, we kept the current along one direction, but we just rotated by 90 degrees this potential, which we work in the simplest situation in which the height of the optical lattice is the same of the average height of the speckles, and the two characteristic lengths are the same. And we got drastically different results in the two cases. So again, this is the mean height of this combined potential, and we see a transition from superfluid to insulator, but the transition happens very rapidly when the current is in the direction of the disordered potential, while it happens much later in the case in which you propagate along the ordered direction. And the reason is relatively simple. To understand, when you propagate along this disordered channels, you can encounter at some point anomalously high speckles. And this, even a single speckle can kill the transfer along all these channels. And that's why if you propagate along the disordered direction, you get very rapidly a killing of the disorder of the superfluidity. Finally, we looked at the case of two-dimensional speckle potential. Okay, so here again, it's as a function of the mean height of the potential. We see a transition from superfluid to insulator. This is a weaker interaction. This is stronger repulsive interactions. And here, well, the bracketing, this is the red lines are the lower bound and the green lines are the upper bound for this case here. In this case, the bracketing is looser, clearly, but still one can get a relatively good understanding of this quantity. In this plot, we also included some Monte Carlo calculations. So the stars are the calculations for the superfluid density from an ab initio calculation of this system, and the agreement is perfect with Gross-Pitayevsky, both for the numerical value of the superfluid fraction and for the bounds, actually. Okay, so this leads me to the last part of the talk. So I introduced these two bounds, and I said that the upper bound is always valid. The lower bound can actually be violated in some cases. So let's see what happens for generic many-body systems. These legged bounds are ideal tools to study with interacting bosons and Josephson junctions. Indeed, I mean, that's especially in the context of Josephson junction, they have been discussed for a long time. And actually, there's been two recent experimental plans. One of those, Francesco Scatta was involved, where they computed the legged bounds indeed to arrays of Josephson junction in superfluid, in unitary fermions and in supersolids. So Leggett introduced this upper bound F+ to discuss supersolidity in solid helium-4 in the 1970s. And in his paper, it's very short and very characteristic paper of Leggett. He concluded that the superfluid fraction of solid helium-4 should be minuscule. He said, right, probably 10 to the -4. And indeed, it was correct. I mean, all the later experiments on the system showed that the system was not super solid. That super solidity has been observed. In the very past few years, we saw an explosion of works in this direction. in particular in spin-orbit coupled Cs in dipolar gases, and now I think there's also some preliminary results on Bose-Bose mixtures. So in these systems, density modulation appears spontaneously in the so-called stripe phase, and well, one can use F plus and F minus to characterize F. For example, this was done in this work here. But there are systems in which instead this legged bounds, especially the lower one, must be handled with care. So for example, if you have a system that has Gaplex excitation at some finite momentum, from Landau criterion, that we know that the sound speed must be basically it's dictated by this Gaplex excitation, and so it must be very low. And then that means that the superfluid density should be strongly reduced. But there are systems that actually in which the energy grows quadratically with this twist, and the density is constant, and therefore both the definition of superfluid density that I gave us before as F, that was just the derivative of E with respect to P naught squared, would give 1, and also the two, since the density is constant, these two bounds will actually give 1 as well. An example of this is ideal bosons. I mean, ideal bosons, you know, they are a system which are condensed, but they're the superfluid, the sound speed is 0 in ideal bosons, and therefore this is clearly not a good superfluid in some sense. Another example is ideal fermions or Lagrangian liquids, which have so-called umklapp modes. So they have gapless modes at 2kF. So in this system, one has to be careful about defining the superfluid density and also this balance. Another class of systems which one needs to take care is the systems that are unstable to small perturbations. So for example, if I take an ideal Fermi gas, you know that I can have the so-called orthogonality catastrophe. So an infinitesimally small perturbation into an ideal Fermi gas causes a system that is completely orthogonal to the one that I had before. In this case, the energy is basically, when you add this small perturbation, the energy becomes completely unaffected by the twist, even though the density remains constant. Another system that displays the same behavior is Luttinger liquid with Luttinger constant K smaller than 3/2. And also another system in which, well, one which I think an interesting system that's to be considered is strongly interacting fermionic mixtures. So there was a recent work by also Stringari in which they computed basically F plus, so this upper bound for a unitary Fermi gas, and they showed that even though it's not a dilute quantum liquid, this F plus remains accurate as long as the wavelength of the optical lattice that you apply is much smaller than the gap delta times m over kf. So when you satisfy this condition, it means that this weak optical lattice is probing only the phononic regime of the dispersion relation, which is linear. And in this case, basically, you're actually only probing the bosonic nature of the field, of the fermionic fluid. Okay, so this brings me to the conclusions. So I've showed that quantum fluids at 0 temperature can have a large normal component when their ground state breaks Galilean or translational invariance. And this lower bounds and upper bounds introduced by Leggett are very easy to compute numerically and very easy to measure experimentally. If you have access to nice photos of your system, you can actually compute them immediately. The upper bound F plus is always valid for arbitrary ground states of many body systems, while the lower bound holds only when your system is fully condensed. So that's the case, for example, in weakly interacting BECs. And these two bounds coincide when we have a one-dimensional configuration, basically. And this F plus and F minus, even in two-dimensional configuration, they still work well in many systems, in many situations that are relevant for ultra-cold experiments. And with this, I conclude. Well, I said we will have a position available in the fall, and I thank you for your attention.
Thank you very much. That was very nice and cool presentation. Are there questions?
in the two definitions, you have that in one definition, you average the direction first and then in the x direction, right? And in the other direction, the x and then the first. But in two directions, how do you find the first and x? It's not. I'm not just. You're not in the two definition. Not only interchanging x and y. If you want, maybe let me. You're actually the two definitions are slightly different. Here you see it's an average over 1 over n, while here it's 1 over the average of n. So it's not just interchanging x and y. Okay. Well, so this are the definitions for as I said before. I will always apply a current along x. So these are the two bounds computed for a current along x. Yeah, so I can basically, if I put the current along x, I will have a lower bound f minus x if you want, and f plus x. But if I put the current along y, I will have two other bounds, f minus y and f plus y, and that will be different from those. Yeah.
Thank you for the talk. So I was wondering whether you can help us complete the supergroup project directly from the, like transverse or longitudinal part of the current function. Directly
Well, as I said, I mean, this definition is basically, I mean, here you are computing the average value of P, and that's related to the current. So. Yeah, yes. I mean, this, what I showed is, yeah, but it's the same. So you're applying a current and you check for the current in the system, basically.
Let's thank Pietro again, and let's go.